In physics, the proton-electron mass ratio is a stubborn anomaly. It is one of the most perfectly measured dimensionless constants in the universe, yet no theoretical framework actually explains where it comes from. According to the National Institute of Standards and Technology, a proton is exactly 1836.15267 times more massive than an electron, but the standard model doesn't predict this number. It simply accepts it. The value is entirely empirical, plugged into equations after the fact to make the math work. Now, a new framework provides the first parameter-free derivation of this ratio, pulling the exact value directly from pure icosahedral geometry. By solving the origin of this specific dimensionless constant, we are forced to reconsider whether particle mass is an intrinsic property at all. This alternative approach is the operationally determined testable bounded timelines, or ODTBT framework. Instead of treating mass as a raw weight, ODTBT models it as a spatial measurement anchored to what are called zero-deviation valleys. In this architecture, fermion masses arise when particles settle into discrete equilibrium positions, valleys, across a 12-dimensional coherence manifold. We can trace the exact proton-electron mass difference through 3 structural levels, eventually calculating the ratio to within 75 millionths of a percent. Within this framework, particle mass appears as a calculable geometric destination. Level 1 establishes the mathematical baseline by calculating the bare geometric basin depths for both particles. These positions aren't guessed. They are extracted using Grant's projection theorem, which translates standard 2-dimensional Pythagorean triples into 3-dimensional markers. The electron seed originates from the 7, 24, 25 triple, locking into the grid at 175/24. The proton seed derives from the 3, 4, 5 triple, dropping into an adjacent position at 12/5. Comparing their spatial depths yields a raw ratio of 1837.49, leaving an error margin of just 0.073%. This calculation relies on exactly 0 free parameters. There are no adjustable variables doing the heavy lifting behind the scenes. Generating a sub-0.1% accuracy strictly through discrete, unfitted geometric markers demonstrates that mass scaling operates purely structurally. Level 1 is highly accurate, but it treats the proton and electron as independent static entities. To close the precision gap, Level 2 introduces a physical interaction known as cross-coupled Euler-Lagrange stationarity. In a dynamic state, these mathematical points interact. They stabilize one another through a mechanism called torsion memory coupling, connecting their phase spaces. Factoring in this mathematical coupling reduces the error margin from 0.073% down to 0.068%. While a 5% improvement to the error rate might seem minor, it serves as mathematical confirmation that cross-coupling physics are actively co-determining the particles' respective mass values. Level 2 transforms the static topological map into an active physical system. To resolve the remaining 0.068% gap, we have to look past the external position of the particles and account for their internal architecture. This brings us to the third and final phase, electromagnetic basin dressing. An electron is an elementary lepton with no constituent parts. Geometrically, it occupies a pure, single coherence channel. Because of this structural simplicity, it mathematically requires 0 correction to its basin depth. The proton is a composite hadron built of 3 valence quarks whose charges sum perfectly to 1. This composite self-energy actively couples to the icosahedral grid, dividing across 10 distinct vertex-edge channels. This carries a mathematical penalty, explicitly reducing the proton's basin depth by a factor of 1 minus the fine structure constant divided by 10. Applying this specific electromagnetic correction finalizes the model. The geometry outputs a definitive ratio, 1836.151. This mirrors the exact observed reality of the universe to an error margin of 75 millionths of a percent. We only achieve this level of extreme theoretical precision when the geometry formally maps the structural difference between elementary and composite particles. This architecture condenses into a single unified equation, forcing 3 fundamental constants to interact directly. The golden ratio drives geometric scaling, pi defines icosahedral symmetry, and the fine structure constant alpha dictates electromagnetic coupling. The mass ratio emerges as the intersection point of the universe's scaling, symmetry, and electromagnetic forces. Any rigorous scientific framework must be stress-tested against new variables to find exactly where its logic breaks. To determine if this geometry acts as a universal mass hierarchy generator for all fermions, researchers executed the muon test. They locked the electron seed into its verified baseline position and systematically scanned the manifold for the heavier muon particle. This chart displays the output from the muon test. The framework failed to maintain its precision, yielding an error of 1.863%. That result is nearly 98 times worse than an independent optimization run, definitively proving that the current geometry does not smoothly generalize across the heavier particle generations. The data yields an honest conclusion. As it stands, the method is an exceptional best pair finder for the proton and electron, but it cannot generate the full standard model hierarchy. Acknowledging exactly where and why a mathematical model fails is what separates verifiable physics from mere numerical coincidence. While the muon test defines a clear boundary, the proton-electron derivation provides a specific case study for geometric mass. The ODTBT framework produces the proton-electron mass ratio to within 75 millionths of a percent without using fitted parameters. The standard model still cannot explain this relationship without leaning on human measurements plugged in after the fact. By deriving particle mass from pure geometry, this model moves away from empirical fitting and towards structural unification.